Okay, so can you hear me? Yeah, so it's my pleasure to introduce Oleg Karpenkov from Liverpool, who will tell us about geometrization of Markov numbers.
Yeah, thank you very much for introducing me and actually for inviting for this workshop. I mean, actually, I like the atmosphere here and the kind of very happy to take part in the research. So I would say that probably I'm one of the first persons from cluster algebras. However, so we have rather significantly was working on Markov numbers. So therefore, probably this talk is more or less the comprehensive answer to Ralph's question, what is Markov numbers for me? What are Markov numbers for me? I will try to explain, and hopefully we could find some links to existing geometry, which I do not see for now. Anyway, so let's go further, and I can probably do it with, oh, I see what the problem. Yeah, so now it works. Yeah, so probably a few words about history. Everything starts with, well, discovery of periodic continuous fractions in general. And then Dirichlet was contributed to approximations of numbers. And actually, the Markov numbers appeared, I think, for the first time as, well, with respect to approximational properties. So in 1872, Markov introduced the spectrum, Markov spectrum itself. And the first results on it was in 1891. Then rather famous uniqueness conjecture. I'm not sure if it is somehow encrypted within cluster algebras, but yeah, so it always exists in 1913. And also probably I should mention that there is also multidimensional Markov spectrum, but again, so I'm not sure if there is something related to mutations or something like that. So therefore, probably, but it's equivalent to Littlewood conjecture, just for you to know. Great, so we wouldn't consider it. Great, so we a little bit extended the Markov tree. More or less, we found several different trees that are parts of Markov spectrum. And our items would be like cone matrices, geometry of continuous fractions, reduction integer matrices. So basically, we would be interested a little bit in what are normal forms of integer matrices up to conjugation by integer matrices. So like Jordan normal forms, but in integer settings. Yeah, and then we have also Mark Eigner's book on Markov theorem and 100 years of the uniqueness conjecture, which actually have a very nice overview of, well, everything that was done, say, in the last century here. Great. So we start with some ingredients, and that would be Markov triples and Markov trees, which you know very well, I guess. So then I will speak about Markov spectrum. I'm not sure if you have heard about that before. So semigroup of reduced matrix is fine. And well, okay, some additional element here. Great, let's start with Markov numbers. So Markov introduced his equation in 1879, and you know it, so probably I will go very fast through it. You know that the solution are triples. And also the good thing about them that these triples can be generated by the following automaton. So you start with any triple, and you rewrite ABC to AB 3A minus C, or you swap any coordinates. So in this way, you can generate all possible solutions of the above Markov equation. Okay, and that's the way how we generate. It turns out that we have a binary tree, except for small steps in the root when something is glued together. But then you have more or less at each vertex, you can either go left or go right or go up. Yeah. So if you use your automaton, you can go in 3 directions here. So it's just you can travel all over this tree. Okay, fine. Now about Markov spectrum. So originally, Markov numbers were defined not with respect to the solutions of this equation, but more as minima of certain forms. So consider indefinite form. Indefinite means that it is a product of two real factors. So determinant of this form is greater than 0, sorry. And basically what we would like to find, we would like to find a kind of, okay, so how does zeros of this form look like? So how do they look like? So basically, this is just a cross, and they intersect at the origin. So basically, what we would like to know, there are some integer points everywhere, and in most cases, integer points are not on the cross. So if we remove the origin, then the natural question to ask, what is the infimum of the value of this form with respect to this integer points? So in some sense, you can think of badly approximable numbers. And here Markov was considered badly approximable forms by integer points. Okay. But then, of course, you can consider some form like, I don't know, 3x squared plus y squared, but you can consider 6x squared plus 2y squared, just multiply everything by 2. Yeah, I mean, this is actually the same cross. I mean, geometrically, that's just the same. Therefore, it would be nice to have some normalization. And the natural normalization here would be a square root of the discriminant. So just divided by square root of the discriminant, and you have a nice, more or less, correspondence between forms and minimas. Yeah, also should I say that if you have SL2Z transformations, they of course will send this cross to another cross, but due to the fact that all the values will be preserved, then the minimum would be also preserved. So small addition to that. Okay. Now Markov spectrum, I think it's a kind of well, I do not like why Markov decided to consider 1 over m rather than m itself. It doesn't too much matter, but it was considered like that. Maybe there was that time possibly they were considering some studies related to resolventes and something like that when they like to have inverses. So yeah, so unfortunately we need to invert that. So example, we have that. So this is the minimum. So square root of 221 is discriminant, and 5 eventually this is minimum for the lattice. Well, this is the simplest what we can have. So here we have square root of 5. Yeah, so it's clear that you can have, if you have 1, 0, you have value 1 here. So this is square root of 5 over 1. Okay. So square root of 5. Okay, so this is actually, in some sense, this quadratic form is the worst approximable because there is no other minimum between 0 and square root of 5. This is the first element of the spectrum. And that's the theorem of Hurwitz. So then you have square root of 8, and that was found by Markov. And then actually Markov managed to write down all the numbers that belong to the spectrum, yeah, that are coming from the product of two forms, their minima, yeah, up to number 3. And his theorem was that if you remove 3, then the set of such numbers would be discrete actually. So the set of such numbers is discrete. Oh, so there is some question probably. Great. Fine. And the only accumulation point here is 3. Okay, so it's discrete outside 3, and the accumulation point is 3. Just for you to know. So this is something what usually have a reference to classical Markov numbers. But of course, you have some Feynman constant that tells that after 4.5, actually all numbers could be represented by some forms. And there is a very interesting spot in between 3 and 4.5 when actually you have some gaps, and they are computed, some of them. But sometimes, so I think Hausdorff dimension is starting to be greater than 0 after you, I mean, if you go further than 3. I mean, it's a very interesting set. Okay. Yeah, we are interested in discrete spectrum, but I mean, the new trees, they would be actually living a little bit in yellow and red zone as well. So now, okay, so another one of the final subjects, which is not related to the previous one, this is matrices and their conjugacy classes in SL2Z. It's a very interesting subject and very natural one. I mean, you have a matrix and you would like to know its Jordan normal form. And that's absolutely fine to get it when you are in complex numbers. Now you start to have some problems when you're in real numbers. And you have severe problems when you go to integers. So like basically this question for SL3Z is a tough question for now. There is no very good description for it. I mean, we can of course do some tautological description, but no nice explanations in terms of geometry. So for SL2Z, we are a kind of in a relaxed situation. Okay, so we can enjoy the theorems. So in the complex case, there are 3 classes only of SL2Z. So complex means you have elliptic rotation. So this is actually matrices of rotation. Yeah, or yeah, you have rotation of order 6, 4. Yeah, okay, 3 and 2. Yeah, degenerate case, this is parabolic matrices. So they are all with the same diagonal elements. So they can be, so any such matrix is, well, integer congruent to that one. And the most interesting case we have for totally real numbers. So when it's hyperbolic case, this is precisely the cross. Yeah. So when we have matrix with 2 eigen lines that kind of, well, that are invariant. Okay. And such classes actually, well, I mean, SL2Z theory is working with the following reduced matrices. So to say formally, you need to consider just to find some matrix with greatest D here, smaller b here, and smaller a or equal a over there. So it's very simple to define. However, I mean, by some reason, because there is a nice structure behind that, which I'm not showing to you, you have the property that the product of such 2 matrices will be again this type matrix. Yeah. So to reduce matrices gives you in the product also reduced matrix. That would be rather important for us. Okay. Yeah, and they're encoded by continuous fractions. But again, so I am skipping that. Yeah. So okay. So they form a semigroup. Yeah. Finally, just one funny operation for you to digest. I start with the definition of continuous fraction, but probably you know what is Euclidean algorithm, so I may skip the step. So just there are 2 ways to write 7/5 in terms of continuous fraction. One will have even number of elements 1 to 1, 1. The second is odd. Well, and basically their relation is that the last element you can write in 2 ways, either n or n plus 1 over 1. Okay. So for quadratic rationalities, so whenever you're considering something a plus b square root of c over d, so you have then pre-period and period. Great. But this is not a kind of a perfect number. A perfect number for me would be the number that doesn't have a pre-period. In some sense, you can think of such numbers actually as of reduced numbers. Yeah, they will be eigendirections of reduced operators. Great. So as long as you have 2 periods, you can define, we call it a normal star summation. What you do, you just make concatenation of the periods. Yeah. So it's a very, very strange operation because, in particular, because it's not well defined, of course. Like you can make 1 star 1, but you can make 1 1 star 1 1, and either you have in the result 1 2 1 2 or 1 1 2 2 1 1 2 2. So maybe already here you see some trace for Markov numbers. So that's precisely what we are doing. We sum up double ones and double twos, and we have well, the next Markov element then. Okay, let's go further. Sorry. Oh, it's not well defined if you think about sequences, because, okay, so have a look here. What does that mean? That here we have infinitely many units. Okay, so okay, so 1 1 means 1 1 1 1 1 1 1. Okay, but this is the same as like that. It is well defined for fixed periods. It's not well defined for a number. Yeah, so it's operation on periods, and as you will see later, actually that's very important that you fix not a number but a period. Yeah, so that's actually the difference between, I mean, what you need to exchange in the standard settings for this kind of mutations, whatever. Anyway, we come back a little bit further to that. So Markov triples and forms. Okay, so first of all, you have these strange numbers, but you say, oh, come on, these are not Markov numbers. I mean, these are just some strange numbers. And I would agree with you. I also completely, how to say it, completely support this statement. But there is some very nice, how to say it, relation between the solutions of the Markov equation. So Markov equation, the standard one, yeah, we see here. And this value. So the number here, the value of the form itself, is actually would be precisely Markov number. But do not forget that we have normalization, and this what the bad thing, what you think is bad, yeah, is nothing else but normalization. So do not forget about discriminant. So after you know discriminant, so your Markov minimum actually is just Markov minimum, nothing else. So now of course, if you want to have element of the spectrum, you need to write down quadratic form, and yeah, so that's the way how you write it. So starting with triple, there is some say algorithm, if you want, to find u and v from these two equations, and then you can write down that form. But we have a nicer version of this form, so do not think about it here. Great, and then we have that one. Now discrete Markov spectra related to continuous fractions. Okay, so for now, let us forget about geometry and just simply start with a sequence. And our sequence would be infinite on two sides. So now we forget that it's one side infinite, but it would be like two sides infinite. And let us allow to cut our sequence in any possible place. And then. So we have sequence. So that's our sequence. We cut it somewhere, and we can write two continuous fractions, one looking towards plus infinity, one looking towards minus infinity. Great, we can compute the sum of these continuous fractions and take supremum of it. I mean, why not? So now we have a nicely defined real valued function on the space of all sequences, on the space of all integer sequences. Yeah, sorry, it's not only, how to say it? I should say that it's not to R, but to R and infinity, of course, to R plus and infinity. Okay, so then there is a proposition, and actually this very nice formula was found by Piron. So who basically said that if you just forget about quadratic forms and do the sequences, then you have precisely the same Markov spectrum. Great. So for instance, if we have periodic continuous fraction like it is here, so we have 2, 2, 1, 1, 2, 2, 1, 1, 2, 2, 1, 1, and we can split it here, for instance, yeah. So 2, 2, 1, 1, 2, 2, yeah, and we need to write this 1, 1, 2, 2, etc. So this is period. Oh, sorry, this would be 2 and then period. Yeah, I mean, so it's written there just like that, yeah. And the period 1, 1, 2, 2, yeah. So then actually that would be the value. In order to check which value you should take for periodic one, it's very simple. You need to compute only, well, I mean, in this case, only 4 different splittings, yeah. 1, 2, 3, 4, because the next one will give you precisely that one. So just 4, nothing else. So it's, I mean, because for the rest you can say, oh, I don't know how to compute infinitely many numbers, but here it's just finite. That's just nice. And for Markov spectrum, we need only periodic ones, probably I should say. Great. Another example with units, which is the simplest one. This is how to compute square root of 5, the Hurwitz number. Great. So now we go to reduced matrices, and let us show how actually why the formula, this very strange formula that we have just seen by Piron, how it's related to actually to eigenvalues of operators, and why actually we do have this minimas. It's actually not very complicated. So let's draw eigenlines and consider the convex hull inside one of the angles. And sorry, then we take the boundary of it. So we take the boundary. We forget about the rest. And yeah, we will take the boundary in any of the angles. So we would like to equip these broken lines with some numbers. And the first number to equip is for every segment. We can compute how many actually smaller segments we have inside. Okay, so it's 3. Here is just 1 there, because I mean you don't see it of course, but the slope there is different actually. It is 2 over here, etc. So now the next step would be to write something for angles. So okay, so we have this segment and that segment, and they actually generate some sublattice. Okay, so we can consider the index of the sublattice, or if you want, determinant of these two vectors. So that would be the integer sign of the angle. Fine. So now we write both, and what we see, the obvious thing that the sequence 2 1 1 3 2 1 1 3 and 2 1 1 3 2 1 1 3, they would be the same because they're just centrally symmetric. Now, not obvious thing that actually you see 2 white here is corresponding to black here. 1 to 1, 1 to 1, 3 to 3, 2 to 2, 1 to 1, 1 to 1. Yeah. So there is another very interesting type duality, which is just valid for continuous fractions. And probably I'm not going to explain further, but just for us, important thing that just this sequence is very nice. So one sequence actually defines the rest sequences. We can consider just it. And yeah, let's forget the colors. So yeah, in this case, we have period 1 1 3 2 by chance, just because, well, I mean, you do not always, of course, have 4 lengths for period. You can have length 21 or whatever. But just because I don't want to draw complicated pictures. Okay, and now if we do with this sequence, if we play the game so who it was, Piron, yeah. So who precisely was considering the below continuous fractions, yeah. So then actually it turns out that that's precisely the Markov entry in the spectrum. So that's actually connection or explanation, if you want, why this formula has something to do with minimas. Okay, I think it was proven somehow separately, but this is a kind of geometric explanation why they're related. Anyway, so reduced operators. Yeah, because of this nice geometric property, we have the following actually theorem for any matrix. Yeah, so when we know the cross, we can have actually k reduced matrices that are integer conjugate to a given one, and they could be easily written just in terms of the period which we have seen on the geometric picture. Okay, fine. So okay, given matrix, you can write period. Sorry, you can build continuous fraction, write all the signs and lengths, consider a period, and this period will lead you to all reduced matrices. That's great. So that are all ingredients for the following picture. Okay, now given some finite sequence, you can think of it as of a period of an infinite one if you want. So what we can do, we can relate it to the matrix, and we relate it via continuance, via certain continuous. So you need to take, well, okay, so k2 n minus 1 means that you take continued excluding the first and the last number. K2n means that here we exclude the first number and take continued. K1 n minus 1 exclude two continued. K1 n is the just continued of the whole. Yeah, just for you to remember. So what is continued? So if you take continued fraction for the whole sequence, that Kn1 would be in the numerator is just the continued, the formula for the continued. I think that one would be in the denominator, or that one. I mean, one of them. Anyway, great. But the good thing that given a sequence, you write matrix immediately. Yeah, okay, sorry. And this is reduced matrix. Yeah, so I have forgotten to say that the matrix would be reduced. The periods here, it's not necessarily if they even, but so if the period is odd, this means that your cross has another symmetry which interchange the cells. Yeah, so this is the difference between SL to Z and GL to Z minus SL to Z. SL to Z is for odd and the rest is for even. Okay. Sorry, SL to Z is for even and the rest is for odd. Yeah. Nice. So now, otherwise, so to go back, so this is our formula. So we take P over A, continued fraction, and also we add this number, and that will go there. So for odd numbers, you have a similar thing. Just I don't want to show it here because so here probably we should restrict only for two odd ones. Yeah. So when you replace cells, there is a little bit, you need to be a little bit careful. Yeah. In our case, it's 1, 1, 2, 2, and you know for Markov tree that's just even. Great. So now how to go to the corresponding form that will give you the minimum. So we introduced a little bit simpler formula than it was in the original Markov theorem. So more or less you can write everything via continuous here. Okay, so BOF, so D. So we do not have nice formula here, but you can go like there, yeah. So E, well, very simple, yeah. So this is E, how to go from matrix to the form. And okay, F, well, it's not very beautiful, but there is some formula, okay. Great, so okay, so this is more or less to say that the objects, sequences, matrices, and forms, they are actually the same. And they will be the same even if you do not start with Markov triple, but you start with some triple. Yeah, I mean, sorry, Markov number, but you can start here with any sequence. So now we go to Markov numbers. And Markov numbers, they are actually, well, so here it's something to take care, I would say. So to go from here to there, we just take brief continuant. So namely, also it's a mistake here, I think. So we should remove one. We should remove the last two here. Oh, sorry about that. Yeah. So there is some typo here. Okay. So Q, how to go back? So this is precisely the uniqueness conjecture. Okay. So basically, given this number, how many sequences can generate it? Yeah. Basically, you have numerator of your Markov number if you want, and you would like to check how many denominators you can also have. Okay, so what would be the sequences? Here, it's very simple. Here, the point of the theory is that the minimal value is attained at 1, 0 for the form. That's how we construct. That's why it is reduced. Yeah, so reduced matrices are not just reduced because it's a nice formula, but it's because they have some nice geometric properties. And indeed, so this is the minimum. And S is of course uniqueness conjecture because yeah, in the Trinity in the top is well just the same. Then about T. So the standard way was considered for con matrices, and they considered raised over 3. However, you can consider just the lower element. It will also give you the correct number. Great. Now Markov element, and well, so here there are some formulas if you want. So that I mean just some formulas. Probably not very interested in them because in cluster algebras you more work with numbers rather than the elements. Yeah, okay. So that's the whole diagram. That's what we have done for Markov numbers. Basically, matrices related to forms related to numbers in a simple way. Well, okay, so in some way, and then there is some implication of this number and of that number. Okay. Great. Now we think a little bit about Markov triples. So if we have numbers, then we can have corresponding periods. Yeah, do not forget that triples are uniquely defined. So numbers themselves not, but triples are. And they imply periods. And also we have con matrices, so these reduced matrices. And it's interesting to know that when we go to the next element, so we should concatenate two sequences of of periods, and the matrices will just multiply to each other. Okay. Well, just let me draw it so together. So we have 1, 1, 1, and now we have new element here 2, which will represent 2, 2. So yeah, okay. So this step is regular. Sorry, I mean, so it's not a concatenation, of course. So actually, for for our Markov trees, we start with that element. So then it is precisely concatenation. So 1 and 2 will be 1, 1, 2, 2. So then you go further. So for instance, we start with these two, and then we add their sum, okay, etc. So this is Markov graph, which we call G of 1, 1, 2, 2. So our idea is to try to replace the units and the twos by some other finite sequences. And we would like to check how the picture with errors that we have seen before, we would like to preserve as much as possible out of it. Okay. So like, for instance, everything is fine for 2, 2, 3, 3. So categorification of Markov tree. Well, okay, so there is a strange notation to say which, so if you have two sequences, which of them is greater. But it turns out after some seminar talks that the simplest way to say if the corresponding continued fraction built on one sequence is just smaller than corresponding continued fraction built on the other one. Yeah, so this is also nice because you can algorithmically decide which is greater. But yeah, I mean, so it's something obvious here. Great. So of course this is smaller than that one because here you have two on odd place. Yeah. Great. So now let us, for a period, let us write inverse period. This is like we go from left to right. Here we go inversely. Yeah. And then also in the brackets, I will write just periodic, how to say it, periodic sequence. So then basically given two sequences, there are three conditions. So first condition is that that one should be less than that one, that inverse should be less than that inverse. Inverse A equals to A, inverse alpha is equal to alpha, inverse beta equals to beta. And also that the minima for just that one and for just that one, just for two, not for the whole tree, but just for two starting elements should be 1. So then we say that if our starting sequences satisfy these conditions, then gamma of alpha beta is a Markov sequence. Well, I mean, it doesn't matter for now, but the important thing to know that there are some other sequences. Like, for instance, you can start with 1, 1, 3, 2, 1, 1, 2, 3, and everything would be fine. So let's say like that. Yeah. So this is our standard tree. And then we can write down, for instance, if we go not with 2s, but with 3s here. So then we have another nicely defined Markov tree, and yeah, and you can define actually the corresponding Markov numbers and everything. I mean, and everything will work. So okay. So here probably I would like to say a little bit more how to define the next triple. I mean the middle element in the triple. Just because I think this is a kind of important for cluster algebras. However, we don't know, we have any idea why, how to say it, what would be the corresponding relation there. Great. So we start with, well, okay. So in the past we started with triple alpha, so A, B, C. So now, unfortunately, we have to add knowledge of the sequence as well. So I would like to keep A with alpha, B with beta, and C with gamma. Like if there is a uniqueness conjecture true for some of the trees, then you can forget this knowledge actually. If you have one-to-one correspondence, that's fine. But for now, we would like to keep. Now, K brief. So K brief would be the numerators of continuous fractions. Yeah. No, oh, sorry, denominators of continuous fractions. Yeah. So they would be everything but the last element of the continuous fraction. Great. So Markov automata operation. Yeah. So as always, we keep 2 and we modify the third one, so which usually corresponds to some mutations, and I don't know what it corresponds here. Now, what would be okay? So here would be just concatenation of 2 sequences that we described before. But what would be this number here? And so Mati actually, so my PhD student, he found a very nice expression for it. It is K brief of double alpha. So you take period of alpha and I mean, so you take 2 periods, write them together and take K brief, and divide over K brief. Yeah. So this number is actually equal to A. So the number in the denominator is A. So, so now for the Markov tree, there is a magic that K brief of A plus A over K brief of A. I mean, these are 2 continuous fractions. I mean, very mysterious one actually. So you write 1, 1, 2, 2, 1, 1, 2, 2, and divide by 1, 2, 2. And by some reason, you will always have 3 times Markov number. Okay, there is a very fine expression. I have never seen it before actually in the literature, so that was probably new. Yeah, of course, if you start from not from 1s and 2s, but from some other numbers, then you have to keep that one. And it's not just because we didn't find the formula, but because actually the formula will have some parameters. Yeah, so like you can check and you see that it's not equal precisely to these numbers. It's very easy to check. Great. So that's basically the how to say it, automaton or mutation operator if you want. But so here we do not have any relations to passes or to something to geodesic or to something. So there is something to look at it, to think a little bit about. Anyway, so minimas. Yeah, I mean, I will skip the theorem because it's not very informative. I would like more to come immediately to the graph, to the picture that we have, to the picture that we have for rather arbitrary sequences. So given any sequence, so now it is 1, 1, 4, 4, 4, 4. Yeah, why not? No 2s anymore. We can just use the same formulas. So it looks like that these formulas are just analytic. You can write them. You can, even if you write here irrational numbers or something else, symbolic one, yeah. So you can write this formula. It's just general. So this interplay is a general thing. The same other way around. So other way around, yeah. So here it's not symbolic because you need to split A over B over A into continuous fraction, yeah. But still, it's fine for for arbitrary how to say it, numbers. Here the same. So you have nice identification of your sequence to to some form. And yeah, so the same, we need to go here. So then also E just the same and F is just the same. So the good thing that this triad, so it is just 3 in 1. Yeah, so this is just, they always come together. So number, matrix, sorry, sequence, matrix, and form. Yeah, now regarding the number. So for the number, we have again a very nice mapping as a continuant, and again, so it's natural states, but the inverse is not true. So the inverse is again a uniqueness conjecture for the corresponding tree. Yeah. So now R. So R is now a tricky thing. We will have this arrow if and only if if the value of the form at 1, 0 provides you minimum, because otherwise you will have another number. so here we should be careful, and here we should pick only the correct trees. Yeah, however, if you work just with continuance and if you disregard that stuff, and probably for cluster algebra representations or whatever, probably you do not need actually forms. So here you work just with sequences. So therefore you can work just with any tree for any sequences. Anyway, yeah. So the same for t. So for t we have minimum, well, minimum defined by this lower lower element. Fine, and then of course you have also a formula which is again analytic continuation to find the Markov value on the spectrum. So everything is just straightforward here. So the non-obvious thing is actually over here. So finally, I would like to say just a few words regarding uniqueness conjecture. If we have our standard Markov tree, then each Markov numbers appears exactly once as maximal element. Okay, so technically, of course, you can have, if you go on sites in the triples, you can have many units, for instance, but unit would be just once when it is maximum. Yes, it's 1, 1, 1 only. Well, 2s and etc. This is a conjecture, and it is actually checked on many examples. And this Eigner's book is a very good description of many attempts to prove this conjecture. And they actually managed to prove it for certain subclasses. I mean, so they proved it for us a large amount of numbers, I would say. It is used in whatever analytic number theory, or so. I mean, no, not analytic, but how it's called, arithmetic number theory. Yeah. Great. So it's another field of mathematics. Generalized uniqueness conjecture, of course, whenever you replace this graph with some others, you can expect that you have something similar. I mean, a similar conjecture, which maybe holds or not. And the good thing about this generalized conjecture, that Matti was able to compute lots of examples, and he has found in one tree, he has found 2 triples when there is the same number appearing. It was a kind of very surprising for us. Okay, so here he states that there is actually a family of such trees when you can find such examples. And this is not deep, so the coincidence is maybe 4 steps. So he didn't go very deep in the computation of the tree. But as you see, the numbers are really huge. So like the thing that they kind of coincide is a kind of a miracle from one point of view. But I mean, so he was not, I would say, too diligent. So therefore, he managed to detect it on the first 100 examples. So from that point, I can think that this is rather oftenly, this has some frequency when the uniqueness conjecture are not true. Just to say more comment about this. So the good thing about this counterexample is that actually that if you think about original uniqueness conjecture and you have some idea that you think you can prove it, yeah, I mean, so then just apply it to these counterexamples, because in many cases this proof will also provide you the proof for the other trees. So it's a kind of nice tasting thing, so to check if your proof is correct or not. And yeah, I mean, so original Markov trees with 1s and 2s, it's still, I mean, in the beginning I thought that a kind of that we should a kind of call now it's not a conjecture but a problem, Markov problem, because I thought that maybe it's not the case, that it is actually true. But after reading the book by Eigner, you see actually that there are many things which have some relation to some Legendre symbols, etc. And so there is something strange which happening is only for that tree, and then probably there is this particular case when you have the conjecture that, I mean, I don't see an evidence that the conjecture has probability not to be wrong, so to be wrong. No, but in the beginning I thought that it's actually confirmed. No, it's yeah, but if it's checked only by the methods which can be disproven by the other one, so then basically conjecture state should be removed and replaced by problem state. But they have much more than we done. So therefore it's, yeah, I mean, I think it's still conjecture. Anyway, so sorry about this philosophy. I mean, yeah, of course it's not relevant to the topic, but I mean, just yeah. And I think that's it for now.
Oleg, let's see whether we have questions. So maybe we will start from the room, and then maybe something will appear in Zoom. So any questions in the room? Ralph? Okay.
You had at some point you had a formula with a
I'm
quotient of two continuants.
I'm going there. Yes, I know that.
Was that only for the Markov tree? Oh, that says that.
Yeah, for the Markov tree. So it's true for the Markov tree. It's but just it happens that if you compute it for Markov alpha, yeah, for say 1 1 2 2 1 1 2 2, it turns out that it would be 3 times Markov number, and just by chance you should put here 3a b minus c. So
there's no analog of this for your generalized.
Yeah, I mean, so okay, so yeah, so in general there is no analog because they will be different. So like here it's always 3a, always 3a, but there you have 3a, 5a, 10a. There are some number. I mean, so you see, so it would be different on different levels. Now the second question, which might be interesting, if there is some tree when you have this analog, and unfortunately we did not pay attention to that question. So yeah, it's worth it. I need to ask Matti, so he probably has some answer to the question. Yeah. Yeah, and also I will answer the question probably which you didn't ask. Are there some equations for Markov numbers? Yeah, similar to that, and because it's the same question actually. So we do not know. These equations also should have this alpha, unfortunately, then at some point. And so it's yeah, equation. Well, equation is something which really so an evidence of some integrability, which should not be the case in general case, I think. So it would be like generating function rather than the precise equation. So sorry, like generating function is not always can be wrapped to the equation. Yeah. Just like that.
More questions from the room? Not at the moment. I see a question in Zoom.
I think it was.
Please.
Oh, hi. Yes, thank you. Actually, my question is also.
Hi.
I didn't quite follow the definition of k-brief. Are you taking the continued the value of the infinite continued fraction given by alpha there?
No. So here, so k-brief from a1 to an. Yeah, it's precisely a continuant of a1 to an minus 1.
Okay, so alpha is a finite string, and you just take
Yes.
the value of the continued fraction up to length n minus 1.
Yes, it's basically not numerator but denominator.
Okay, fine. Okay.
So it's and here, so that's why it's reasonable to here consider alpha plus alpha. Yeah. So it's not our normal star, but it's just a concatenation.
Yes. Okay. All right. Thank you.
Oh, hi. Yeah.
More questions in Zoom, maybe? But I didn't switch on. I didn't turn on. Now I don't know. Okay. So just again, are there any other questions in the Zoom? Jin has more. Okay.
Yeah, just one other vague question. I remember here listening to Ralph talk about the Markov connections with Markov conjecture several years ago, and he's there so he can correct me, but I remember that he had some kind of snake graphs associated the sequences just with 1s and 2s. So do you have some snake graphs here when you allow more general sequences?
Yes, indeed. So I was also very interested to speak with Ralph with respect to this, how to say, thing, and the kind of so I knew this about snake graphs only from him, unfortunately. So I didn't have time to think about it, but from what I have seen, so the Markov numbers appear a little bit differently there. So, but yeah, so it's again, so it's a very good question, which may be not very how to say it correct one, if this generalization can also somehow be interpreted in terms of some snakes.
Yeah, so as I remember, the sequences of ones and twos were they Sturmian words? They were special kinds of words in 1 and 2, not arbitrary.
Yeah, because you can, it's Sturmian words. They are precisely obtained by concatenations. Yeah. So I mean, the words should be the same as here. Yeah, am I correct? I think the words, the Sturmian words, they are I might be wrong. I don't know. So I mean.
Right, but it looks like you're allowing arbitrary collections of 1s and 2s. I mean, I think this.
For the tree, for a particular tree, you do not have, of course, arbitrary collection because you have.
Right. Okay.
You have 1, 1, 2, 2.
Yes.
Then you can write in between 1, 1, 2, 2. Then you can write in between 1, 1, 1, 1, 2, 2, and here 1, 1, 2, 2, 2, 2. And probably you would never have 1, 1, 1, 1, 2, 2, 2, 2.
Okay.
So it's not arbitrary. So
your automata is responsible for producing the
yes.
Sturmian words essentially.
Yes. I think so. Yeah, I think so. No, but with respect, that is fine. But so the snakes, I mean, the feature of the snakes that they have this combinatorial numeration when you put some things. Yeah. And if you replace 1s by 3s, for instance, 2s by 3s, so then I mean maybe Ralph can tell, but I do not see how it. No, but if you have sequence of 1s and 3s, yeah. So there are some snakes there. Okay, so Ralph is saying that there are some snakes there. Just. Okay. But then probably we will need to discuss that later.
Thank you.
Yep.
Okay, thanks. So more questions on Zoom? Cannot see. More questions in the room? No, then let's thank Alan.
Thank you.
See you all in the next event.